Closed loop transfer function. Once the model of motors are known, feedback path can be added to obtain the desired output response. To change the open loop arrangement of the separately excited DC motor, as shown in the figure, into a closed loop system, a speed sensor is connected to the output of the shaft. The output of the sensor, which is proportional to the speed, is amplified by a factor K1 and is compared with the reference voltage VR to form the error voltage VE, and that is shown in the block diagram by simply modifying this block diagram. Now this is a closed loop block diagram. Without this feedback system, this is a open loop. With this feedback system, this will become the closed loop block diagram for separately excited DC motor drive. Now the closed loop step response due to the change in the reference voltage can be found with the disturbance of the load TL of S equals to 0. Then the transfer function will become omega S divided by V R of S equals to K2 kV IF divided by Rm into B divided by S square tau A tau M plus S tau A plus tau M plus 1 plus kV IF whole square K1 K2 kV IF divided by RMB. Let it be equation number 1. Now, the response due to the change in the load torque TL can also be obtained by setting VR equals to 0. Then the transfer function will become omega of S divided by TL of S equals to minus 1 by B S tau A plus 1 divided by S square tau A tau M plus S tau A plus tau M plus 1 plus kV IF square plus K1 K2 kV IF divided by Rn into B. Now, by using the final value theorem, the steady state change in the speed delta omega can be found due to the step change in the control voltage delta VR and the step change in the load torque delta TL can be found respectively by substituting S equals to 0 in the above equations. Then this will become K2 kV IF divided by RMB plus kV IF whole square plus K1 K2 kV IF, the whole thing multiplied by delta VR. That is equation number 3. This comes from equation number 1. Then delta omega equals to minus of Rm divided by RMB plus kV IF square plus K1 K2 kV IF whole thing multiplied by delta TF. That is equation number 4. This block diagram uses a speed feedback only, but in practice the motor is required to operate at a desired speed, but it has to meet the load torque, which depends on the armature current. While the motor is operating at a particular speed, if a load is applied suddenly, the speed will fall and the motor will take time to come up to the desired speed. A speed feedback with an inner current loop provides fast response to any disturbance in lead command, load torque, and supply voltage. A speed feedback with an inner current loop, as shown in this figure, provides a faster response to any disturbance in the speed command, the load torque, and supply voltage. The speed control from 0 to base is normally done at the maximum field by armature voltage control, and the control above the base speed should be done by field weakening at the rated armature voltage. In the field control loop, back EMF EG is compared with the EG reference, which is generally is about 0.85 to 0.95 of the rated armature voltage. If the speed is below base speed, the field error here EF is large and the field controller saturates, thereby applying the maximum field voltage and the currents. When the speed is close to the base speed, VA is almost nearer to the rated value and the field controller comes out of the saturation. For a speed command above the base speed, the speed error causes higher value of VA and the motor accelerates. The back EMF EG increases and the field error EF is going to decrease. If this increases, this will be decreased. The field current then decreases and the motor speed continues to increase until the motor speed reaches the desired speed. Thus, the speed control above the base speed is obtained by field weakening, while the armature terminal voltage is maintained at nearer to the rated value. In the field weakening mode, the drive responds very slowly due to the large field time constant. A full converter here is normally used in the field because it has the ability to reverse the voltage, thereby reducing the field current much faster than that of the semi-converter. For current loop is used to cope up with the sudden torque demand under transient conditions. The output of the speed controller EC is applied to the current limiter, which sets the current reference IA reference for the current loop. The armature current IA is sensed by the current sensor, filtered normally with the active filter to remove ripple, and compared with the current IA reference. The error current is processed through current controller, whose output is VC, adjusts the firing angle of the converter and brings the motor speed to the desired value. Any positive speed error caused by an increase in either speed command or low torque demand will produce high reference current IA reference. The motor will accelerate to correct the speed error and finally settles at a new IA reference, which makes the motor torque equal to the load torque, resulting in a speed error close to zero. For any large speed error, the current limiter saturates and limits the reference current IA reference to a maximum value of IA max. The speed error is then corrected at the minimum possible armature current, that is IA max, until the speed error becomes small and the current limiter comes out of the saturation. Normally, the speed error is corrected with IA less than possible value of IA max, which means for the speeds lower than the base speed, the current limiter, this part is going to work to make the speed correction, and when the speed is more than the base speed, this part is going to work. That speed variation caused by the load demand or torque demand. And this is the circuit for closed loop speed control with inner current loop and field weakening. So this is regarding the closed loop transfer function. If this video is useful, please like, share and subscribe.